Welcome back. In this lecture, I will work out few more example problems and I will also give answers to the questions given in the last lecture. So, the first let us go to the first problem. The first problem is like this: in a R22 based refrigeration system, a liquid to suction heat exchanger with an effectiveness of 0.65 is used. The evaporating and condensing temperatures are 7.2 degrees centigrade and 54.4 degrees centigrade respectively. Assuming the compression process to be isentropic, find specific refrigeration effect, volumic refrigeration effect, specific work of compression, COP of the system, and finally compressor exit temperature. And comment on the use of liquid suction heat exchanger by comparing the performance of the system with a SSS cycle operating between the same evaporator and condensing temperatures. That means basically it is a single stage system. We have to make performance comparison between a system with liquid suction heat exchanger and a system without liquid suction heat exchanger. Both of them are operating between the same evaporator and condensing temperatures. Now, let us see how we can work it out. So, the given information is like this: refrigerant is R22, evaporator temperature is 7.2 degrees centigrade, condenser temperature is 54.4 degrees centigrade, and effectiveness of liquid suction heat exchanger is 0.65. So, this is the schematic of the system. As you have already studied this. You can see that again you have the 4 basic components: evaporator, compressor, condenser and the expansion device. In addition to this, we have the liquid suction heat exchanger, and as you know, in the liquid suction heat exchanger, the refrigerant liquid that is coming from the condenser, that means this liquid, this gets subcooled, and subcooled liquid enters into the expansion device. At the same time, the vapor that is going to the compressor, low temperature low pressure vapor going to the compressor, gets superheated in the liquid suction heat exchanger and enters into the compressor in a superheated state. Okay. So, basically the liquid, since it is at a higher temperature, it exchanges heat with the low temperature vapor and it gets subcooled and the vapor gets superheated. So, here the cycle is shown on pH diagram. Here cycle 1, 2, 3, 4, 5, 6 is a cycle with liquid suction heat exchanger, and the cycle 1, 3 dash, 4 and 6 dash, as you can see, is without liquid suction heat exchanger. Okay. So, here we have made one assumption which is not mentioned in the problem. We assume that for both the cycles, the exit condition of the evaporator is saturated vapor. Similarly, the exit condition of condenser is saturated liquid. Okay. So, these two are the common conditions for both the cycles. Now, from the definition of effectiveness of heat exchanger, we can write, as you know, effectiveness as Q actual divided by Q maximum, and Q actual in this case is MCP minimum into delta T actual divided by MCP minimum into delta T maximum. And for our this thing, you can see that this is a liquid suction heat exchanger, and what is the fluid that has lower MCP? You can see that on one side you have vapor, okay, on the other side you have liquid, and the mass flow rates are same. Okay. So, you have MCP of liquid and MCP of vapor. Okay. MCP of liquid is the hot stream and MCP of this vapor is a cold stream, and mass flow rate is same because same mass is flowing throughout the circuit. So, we can see that the vapor is having the minimum MCP of V, because Cp of vapor is always lower than Cp of liquid. So, as a result, MCP is minimum for the vapor. Okay. This is the minimum for vapor. Okay. So, if this is minimum for vapor, we can define heat exchanger effectiveness as effectiveness of heat exchanger is, as you know, MCP minimum into delta T actual. And what is the delta T actual? Delta T actual is nothing but T2 minus T1, that is the actual temperature change of the vapor, divided by MCP minimum into delta T maximum. Here the delta T maximum is a difference between the maximum temperature, which is nothing but the outlet temperature of the condenser, and the minimum temperature, which is the outlet temperature of the evaporator. So, MCP delta T maximum is T4 minus T1. Okay. So, these MCP get cancelled. Finally, you find that effectiveness of heat exchanger is simply given by T2 minus T1 divided by T4 minus T1, and from the data we know T1 and we also know T4. So, T1 and T4 are known to us, and effectiveness is given as 0.65. Okay. So, we can find out what is the exit temperature T2. So, that is what is done here. The effectiveness is given by T2 minus T1 divided by T4 minus T1. This is equal to 0.65 as given in the input. So, from this you find that T2 is equal to T1 plus 0.65 into T4 minus T1, which works out to be 37.88 degrees centigrade. Okay. Then from energy balance across liquid suction heat exchanger, you can write H2 minus H1 is equal to H4 minus H5, because mass flow rate is same for both hot and cold streams. Okay. So, enthalpy difference across the heat exchanger must be same for hot and cold streams. As a result, you can write H5 as a function of H4, H2 and H1, that is H5 is equal to H4 minus H2 minus H1. So, we will be using these two values or these two expressions for obtaining the state properties. Now, as we have done in the last lecture, the first thing we do is we find out the various properties at all the state points. Okay. So, let me first once again show the state points. So, state point 1 is the outlet of the evaporator, and which is saturated in saturated condition, and the temperature is 7.2 degrees centigrade. Okay. And state point 2 is the exit condition of the liquid suction heat exchanger, and it has a temperature of 37.88 as we have now just now computed. And process 2 to 3 is, as you know, is compression process, and here we are assuming the compression process to be isentropic. Okay. That means S2 is equal to S3, right. So, 2 to 3 is the isentropic compression process, and 3 to 4 is the heat rejection in the condenser. Okay. So, this is the condenser, as you know, and we know that point 4 is a saturated liquid condition at condenser pressure, and condenser is operating at a temperature of 54.4 degrees centigrade. So, we can find out the condenser pressure. Okay. So, point 4 is a saturated liquid at this pressure. So, we can find out the properties at this point, and 4 to 5 is what is happening in the liquid suction heat exchanger, and as you can see that during the this process, the 4 to 5, the hot liquid, refrigerant liquid loses heat to the cold vapor. Okay. So, there is a heat transfer in this manner. The heat transfer rate is QLSHX. So, there is an exchange of heat between the hot stream and the cold stream. So, due to this, the refrigerant liquid temperature drops from 4 to 5, and the vapor temperature increases from 1 to 2. Okay. So, point 5 is now in the subcooled region, and the process 5 to 6 is isenthalpic expansion process in the expansion device, isenthalpic process in the throttling process. Okay. And 6 to 1 is the heat extraction in the evaporator, okay, at 7.2 degrees centigrade, right. So, these are the points, and as I have already told you, cycle 13-46- is for an SSS cycle without a liquid suction heat exchanger. Okay. So, compression processes, both the compression processes are isentropic, that means S1 is equal to S3- and S2 is equal to S3, okay, as I have already mentioned. Similarly, processes 4 to 6- and 5 to 6 are isenthalpic, that means H4 is equal to H6- and H5 is equal to H6. Okay. Now, from the given input values and this information, we can find out all the state points. So, state point 1, as I have already told you, is the exit of the evaporator, which is a dry saturated vapor at 7.2 degrees centigrade. So, at this point we find the saturation pressure to be 6.254 bar, and quality, as you know, is 1. So, we give these two as the input and we find rest of the properties. So, we find the pressure, we find the enthalpy 407.6, entropy 1.741, and specific volume 0.03773. Okay. Point 2 is the exit of the liquid suction heat exchanger. Okay. So, here again the pressure remains same because it is an isobaric heating process. So, pressure is same as point 1, and temperature we have found from the effectiveness of heat exchanger as 37.88. So, using this pressure and temperature information we can find out rest of the properties. Okay. So, from these two values we find the enthalpy to be 430.7, entropy to be 1.819 and specific volume to be 0.04385, and obviously this is in superheated region. And 0.3 is the exit condition for the compressor. Okay. So, it is compressor exit. So, what do we know at this point? At this point we know the pressure, because this is nothing but the saturation pressure at 54.4 degree centigrade, and we also know the entropy, because this is an isentropic process. So, S3 is equal to S2. So, from the known values of pressure and entropy we find the other properties like enthalpy and temperature. So, temperature works out to be 104.9 and enthalpy is found to be 466.8 kilojoule per kg. Then 0.4 is nothing but the exit of the condenser, which is saturated liquid. So, quality is 0, temperature is 54.4. So, we can pressure is saturated pressure 21.46 bar, and from this information you can find out what is the enthalpy 269.5 and entropy. Okay. Then 0.5 is nothing but the exit of the liquid suction heat exchanger on the liquid side. So, this we have we are obtaining using the energy balance, as I have already explained, across the liquid suction heat exchanger. So, we find this enthalpy from the enthalpies of H4, H1 and H2. Okay. So, because the enthalpy difference for hot and cold streams are same. So, this works out to be 246.4 kilojoule per kg, and from the pressure value and enthalpy value we can find out what is the temperature and what is the entropy, and this is in subcooled region. And 0.6 is the exit of the expansion device. So, its temperature is same as the evaporator temperature 7.2 degree centigrade, pressure is same as the evaporator pressure 6.254 bar, and we need another additional information. That information is provided by the isenthalpic process. The enthalpy at 0.6 is same as enthalpy at 0.5, which is equal to 246.4. So, using the enthalpy value and pressure value we can find out what is the entropy, and you can also find out what is the quality of the refrigerant vapor, okay, which comes out to be 0.1903. And 0.6 dash is for the SSS cycle without liquid suction heat exchanger. So, here again the temperature is 7.2, pressure is 6.254, and the enthalpy here is the enthalpy at the exit of the condenser, that is 269.5. Okay. So, again from the enthalpy value and the pressure you find the entropy value, and you also find the quality, which works out to be 0.3063. And 0.3 dash is for the again SSF cycle without liquid suction heat exchanger. At this point we know that the pressure is 21.46 and entropy is same as the entropy at the exit of the evaporator, that is 1.741. So, this entropy, using the entropy value and the pressure value we can find out what is the enthalpy and what is the temperature. Finally, 0.1 dash. 0.1 dash is your saturated liquid at this condition. You can see that the temperature is 7.2 and quality is 0. So, this is a saturated liquid condition at evaporator pressure. So, from this information you find the enthalpy to be 208.5 and entropy to be 1.030. So, this is a major task. Once you find all the properties, then we can easily find out the required performance parameter by applying energy balance across each component. Okay, that is what we will be doing. So, first let us find the results for with liquid suction heat exchanger. So, refrigeration effect is nothing but H1 minus H6. You can see that with liquid suction heat exchanger, this is the refrigeration effect H1 minus H6, and the work of compression is this H3 minus H2, and the exit inlet temperature to the compressor is at 0.2, exit is 0.3. Okay. So, refrigeration effect H1 minus H6, if you substitute the values you find that it is 161.2 kilojoule per kg, and volumic refrigeration effect is nothing but, as you know, refrigeration effect divided by the specific volume at that point. Okay. So, specific volume we have found from the properties. So, if you substitute the specific volume value there, you find that the volumic refrigeration effect is 3676.2 kilojoule per meter cube. Third is work of compression is nothing but H3 minus H2, and both the enthalpies are known to us. So, you find that work of compression is 36.1 kilojoule per kg. and then finally FOP is H1 minus refrigeration effect divided by work of compression, that is H1 minus H6 divided by H3 minus H2, which works out to be 4.465. Then temperature at compressor exit, we find this from the pressure and the entropy values. You find that it is almost 105 degrees centigrade, it is 104.9 degrees centigrade. Okay. So, this is the performance with the liquid suction heat exchanger. Now, let us find out the performance without liquid suction heat exchangers. Again, what we do is we apply the energy balance across evaporator, compressor, condenser, etc., and then find out the required parameters. Okay. So, without liquid suction heat exchanger, as you know, the cycle I have already told you is 1, 3 dash, 4, 6 dash. So, the refrigeration effect is now H1 minus H6 dash, and work of compression is, this is work of compression, H3 dash minus H1. Okay. You can see anyway, let me point out at this point, and this I have already discussed in the earlier lectures. When you are using a liquid suction heat exchanger, what is happening is the compressor inlet is entering into the superheated region. This is your superheated region. So, you can see that point 2 is in superheated region, whereas with SSS cycle the compressor inlet is a saturated vapor. Okay. So, this will have a bearing on the performance, which we shall see shortly. So, refrigeration effect is H1 minus H6 dash, which comes out to be 138.1 kilojoule per kg, and volumic refrigeration effect is H1 minus H6 dash divided by V1, which works out to be 3660.2 kilojoule per meter cube. Work of compression is H3 dash minus H1, which is equal to 31 kilojoule per kg, and COP is found to be 4.455, and the temperature at compressor exit from the pressure and entropy values is found to be 74.23 degrees centigrade. Okay. So, this is the performance without liquid suction heat exchanger. So, let me show the comparison now. So, this table here shows the comparison for the same evaporator and condensing temperatures. What is the performance with and without liquid suction heat exchanger? First thing you can see is that when you are using a liquid suction heat exchanger, your refrigeration effect is increasing. That means the required mass flow rate will reduce. Okay. So, this is a plus point. Second plus point is that the quality of vapor at the evaporator inlet has reduced. Okay, it is 0.1903 with liquid suction heat exchanger and 0.3063 without liquid suction heat exchanger. Okay, this is also a plus point. This is happening because the entry to the expansion device is now in subcooled region. As a result, you have less vapor. Okay, and volumic refrigeration effect has, there is a marginal increase. Okay, it is almost same. You can see that this is 3676, this is 3660. Okay, so it is almost same. So, why volumic refrigeration effect is remaining same even though specific refrigeration effect has increased? This is because the inlet condition to the compressor with liquid suction heat exchanger is in superheated region. So, once it goes into the superheated region, its specific volume increases. Okay, density reduces, so specific volume increases. So, the expression for volumic refrigeration effect, as you know, is nothing but the ratio of refrigeration effect divided by the specific volume. Okay. So, with liquid suction heat exchanger, both the numerator and as well as denominator, both of them increase. Okay. So, ultimately whether the volumic refrigeration effect increases or not depends upon the relative increase of these two parameters. Okay. So, you may not get a large benefit when you have a large superheat. In fact, that is what is shown here. Okay. Then work of compression. Work of compression, obviously with liquid suction heat exchanger, work of compression has increased because the isentropes in superheated region are flatter compared to the isentropes closer to the vapor dome. So, this is 36.1, this is 31. So, this is actually a negative this thing, and COP you can see that is almost same. Okay, it is 4.465 with liquid suction heat exchanger and it is 4.455 without liquid suction heat exchanger. Okay, this is because COP, as you know, is the ratio of refrigeration effect divided by work of compression. So, when you are using liquid suction heat exchanger, refrigeration effect is increasing, work of compression is also increasing. Okay. And without liquid suction heat exchanger, this is less, at the same time work of compression is also less. Okay. So, as a result, the net difference between these two is not much. Okay. And however, one significant difference between the system with liquid suction heat exchanger and without liquid suction heat exchanger is in the discharge temperature. Okay. you can see that with liquid suction heat exchanger discharge temperature is about 105 degree centigrade, whereas without liquid suction heat exchanger it is about 74 degree centigrade. That means almost more than 30 degrees increase. Okay. So, this is definitely a negative point as far as the liquid suction heat exchanger is concerned. Okay. So, you have when you are using liquid suction heat exchanger, particularly for R22 systems, there are some benefits and there are some disadvantages. Okay. So, ultimately depending upon your requirement, one has to decide whether liquid suction heat exchanger is required or not. Okay. And one thing I would like to point out here is that the results or the trends may not be same for all the refrigerants. It may vary from refrigerant to refrigerant. Okay. For some of the refrigerants, liquid suction heat exchanger is found to be beneficial. For example, for systems like R12, liquid suction heat exchanger is good. Okay. But for R22, it offers certain advantages and certain disadvantages. Okay. So, ultimately a trade off is required between the benefits and the disadvantages. Okay. Now, let me discuss the second problem. This is a problem on Vapour absorption refrigeration system. So, let me read the problem. A Vapour absorption refrigeration system based on water lithium bromide has a refrigeration capacity of 300 kilowatts. The system operates at an evaporator temperature of 5 degree centigrade and a condensing temperature of 50 degree centigrade. The exit temperatures of absorber and generator are 40 degrees and 110 degree centigrade respectively. The concentration of solution at the exit of absorber and generator are 0.578 and 0.66 respectively. And it is also mentioned that we can assume the effectiveness of the solution heat exchanger to be 100%, exit condition of refrigerant at evaporator and condenser to be saturated. That means you have saturated vapor at the exit of evaporator and saturated liquid at the exit of condenser. Okay. The third assumption is that the condition of the solution at the exit of absorber and generator are at equilibrium. Okay. That means absorber exit and generator exit, you have equilibrium solutions. And enthalpy of solution at the inlet to the absorber may be obtained from the equilibrium solution data. Okay. That means for obtaining the enthalpies of these 3 points, that is at the exit of absorber and generator and also at the inlet to the absorber, can be obtained from the equilibrium HTX data. That is what it means. And the enthalpy of superheated water vapor can be obtained from this equation. HV is equal to 2501 plus 1.88 T, where HV is in kilojoule per kg and T is in degree centigrade. Okay. So, this is the information given, and from this information we have to find out the mass flow rates of refrigerant, weak and strong solutions, heat transfer rates at the absorber, evaporator, condenser, generator and solution heat exchanger, COP and second law efficiency, and finally solution pump work. And for obtaining the solution pump work, we can take the density of solution to be constant at a value of 1200 kg per meter cube. Okay. Okay, let me summarize the information given. Refrigeration capacity is given to be 300 kilowatts, evaporator temperature 5 degree centigrade, condenser temperature 50 degree centigrade, absorber temperature 40 degree centigrade, generator temperature 110 degree centigrade, weak solution concentration zeta Ws is 0.578 and strong solution concentration zeta Ss is 0.66. Effectiveness of solution heat exchanger is 1 and density of solution is 1200 kg per meter cube. So, this is the information given. So, now let me once again I have already explained this while discussing Vapour absorption refrigeration systems, but let me once again quickly explain the system and show the various state points. Okay. So, as you know, we have the evaporator here, this is the evaporator, this is the absorber, this is the generator and this is the condenser. In addition, you have the expansion device for the refrigerant and you have the expansion device for the solution, you have the pump for solution and this is solution heat exchanger. Okay. And as you know, the working this thing low temperature low pressure vapor at 0.4 enters into the absorber, it comes in contact with strong solution coming from the generator at point 10. So, the solution absorbs this vapor and heat of absorption is taken out QA, and the resulting weak solution is pumped in this pump to the high pressure, and the high pressure weak solution flows through the solution heat exchanger where it is preheated by taking heat from the hot solution coming from the generator, and this preheated solution which is weak, that means which is strong in refrigerant, goes to the generator where heat is supplied to the solution. As a result of this heat supply, refrigerant is separated from the solution. So, refrigerant at high pressure and high temperature goes to the condenser. In the condenser it condenses and the heat of condensation is rejected to a cooling water or a heat sink, and the condensed refrigerant liquid at high pressure is throttled in the expansion device to low pressure, and because of this the pressure and temperature drops. So, this low pressure low temperature refrigerant is sprayed into the evaporator where it evaporates taking heat from the external heat source. So, you get the useful refrigeration effect QE, okay, and the cycle continues, the vapor goes to the absorber and the cycle continues, and the solution which is now stronger in absorbent and weaker in refrigerant at 0.8 flows through the solution heat exchanger, then the expansion device, and is then sprayed into the absorber so that it can again absorb the refrigerant vapor. Okay. So, again look at the points. Point 1 is the exit of the generator, where it is pure refrigerant vapor at high pressure and high temperature at the exit of the generator. Point 2, okay, point 2 is the refrigerant liquid at high pressure, saturated refrigerant liquid at high pressure, and it is at the exit of the condenser. Point 3 is a low pressure refrigerant at evaporator pressure, and point 4 is low temperature low pressure saturated vapor. Point 5 is weak solution at evaporator pressure. Point 6 weak solution at generator pressure. Point 7 preheated weak solution at generator pressure. Point 8 strong solution at generator pressure and generator temperature. Point 9 is strong solution, so now cooled strong solution still at high pressure. Point 10 is the strong solution at evaporator pressure. Okay. So, now we will find out the properties of all these points, because if you want to find out the performance we need to know the properties. Okay. So, for finding the properties we make the assumptions that the refrigerant vapor at generator exit to be in equilibrium with solution leaving generator. Okay. This assumption is required to find the enthalpy of the refrigerant vapor. Okay. That means it is given that the solution leaving the generator is at 110 degree centigrade. Since the vapor is at equilibrium with this, vapor also has a temperature of 110 degree centigrade. So, once you know this, you can find out the enthalpy of the vapor, because it is given that enthalpy of the vapor can be obtained from the expression 2501 plus 1.88 into T, where T is 110 degree centigrade. So, from that expression you find that the enthalpy of vapor at generator exit is 2708 kilojoule per kg. Okay. Then from the effectiveness of solution heat exchanger, again effectiveness, as you know, is defined as the MCP minimum into delta T actual divided by MCP minimum into delta T maximum. In this case the mass flow rate of the strong solution is less than the mass flow rate of the weak solution, and if you assume that the CP values are almost same, then you find that it is the strong solution which has the lower MCP product. As a result, the effectiveness of heat exchanger is defined in terms of the strong solution flow rates and strong solution specific heat. Okay. So, you can write effectiveness as MSS into CPSS into delta T actual, which is T8 minus T9, divided by MCP of strong solution into delta T maximum, which is equal to T8 minus T6. And it is given that this value is equal to 1, because this heat exchanger is 100% effective. So, from this you can easily show that T9 is equal to T6 is equal to 40 degree centigrade, because T8 and T8 it is very easy. T6 is given to be 40 degree centigrade. Now, you can use the property charts and find the properties. Okay. Remember that I have discussed PTX and HTX chart. So, to find this property we will be using PTX and HTX charts in addition to the refrigerant properties. Okay. Let me quickly go through how properties have been evaluated. point 1 is at the exit of the generator, and this is pure refrigerant vapor. At this point we know the pressure, okay, because this pressure is nothing but the saturation pressure corresponding to the condensing temperature, okay, which is equal to 50 degrees. So, this pressure is known to us and temperature is known to us. So, from this we have found the enthalpy, okay. And point 2 is the exit of the condenser, as I have already discussed. It is saturated liquid. So, we know the temperature to be 50 degrees centigrade and the pressure is saturated pressure at 50 degrees, which is equal to 123.3 millibar. So, from this equation you find the enthalpy is equal to 209 kilojoule per kg. Point 3 is the exit of the expansion device. So, the temperature is same as the evaporator temperature, pressure is equal to evaporator pressure, and the enthalpy is same as the inlet enthalpy, which is equal to 209. Okay. So, we know the enthalpy, and point 4 is nothing but the exit of the evaporator. So, we know the temperature 5 degrees and pressure is 8.72, and we know that at this condition it is dry saturated, okay, that means quality is 1. So, from this information find out the enthalpy of saturated vapor at 5 degrees centigrade, which is 2510 kilojoule per kg. Point 5 is now solution, okay. This is the weak solution leaving the absorber, and what do we know at this condition? We know that the temperature is 40 degrees centigrade and the pressure is same as the evaporator pressure, that is 8.72, and it is also mentioned that the concentration is 0.578, okay. So, this is given as the input, concentration is given as the input, temperature is given as the input. So, using the concentration and temperature and concentration data, you can find out the enthalpy values from equilibrium HTX chart, okay. Now, point 6 is nothing but the exit of the solution pump, and if you assume that the solution pump work is negligible, then you find that the enthalpy remains same as the inlet enthalpy, okay. That is the reason why we have taken enthalpy as minus 154, and the pressure will be obviously the condensing pressure, that is 123.3, and there is no mass transfer. So, concentration remains same, that is 0.578, and point 7 I will explain to you. Point 7 is nothing but the condition of the weak solution at the exit of the solution heat exchanger. All that we know about point 7 is that the pressure is 123.3, and we also know the mass fraction, which is equal to 0.578, but this information is not adequate to find the enthalpy, okay. So, this enthalpy has to be obtained from energy balance, okay. I will show you the energy balance equation. Then point 8 is the strong solution condition at the generator exit. So, at this point we know the temperature to be 110 degrees centigrade, and we also know the concentration to be 0.66. So, from the temperature and concentration data we find the enthalpy to be minus 13 kilojoule per kg, and pressure is of course same as condensing pressure, and point 9 is the exit of the solution heat exchanger, and from the solution heat exchanger effectiveness we find that this temperature is same as 0.6, that is 40 degrees centigrade. So, we know the temperature and we also know the mass fraction, okay. And if you assume that you can use the equilibrium HTX chart, from this and this you can find out the enthalpy, which is equal to minus 146, okay. So, that is how we find the enthalpy, and point 10 finally is nothing but the exit of the solution expansion device, and if you are assuming this expansion process to be isenthalpic, enthalpy will remain same as minus 146, and we also know that the concentration is 0.66 because there is no mass transfer, and pressure is same as the evaporator pressure, that is 8.72, okay. So, once you have all the points and once you have the PTX and HTX charts, then if you can locate the points carefully on the PTX and HTX chart, then you can find out all the required state point property data, okay. Once you have all the property data, the problem becomes very simple, because all that you have to do is take each component and apply mass and energy balance across each components. So, in you might have noticed that one of the major tasks is to obtain the correct property values, okay. If you do not get the correct property values, final answers will be wrong, okay. So, for that reason you should know the cycle properly, okay, and if you can plot the cycle on pH or TS and locate the point, then it becomes easier, okay. So, once we have the properties, we can quickly find out the required mass flow rate of refrigerant. We apply energy balance across the evaporator. This is nothing but steady flow energy equation, and we assume kinetic and potential energy changes to be negligible. So, mass flow rate is simply equal to QE divided by H4 minus H3, which is equal to 0.1304 kg per second, okay, because QE is given to be 300 kilowatts, and H4 and H3 we have obtained. Then circulation ratio, because we have to find out the mass flow rates of strong and weak solutions. So, first let us find the circulation ratio. Circulation ratio, as you know, is defined as the ratio of strong solution flow rate divided by the refrigerant flow rate. Okay. And from mass balance across the absorber, we have seen that for water lithium bromide systems, the circulation ratio is equal to concentration of the weak solution divided by the difference between the strong and weak solution concentrations, that is zeta Ws divided by zeta Ss minus zeta Ws. Okay. And zeta Ws from the input data is equal to 0.578 and zeta Ss is 0.66. So, if you are substituting these values, you find that the circulation ratio is 7.05. So, once you know the circulation ratio, you can easily find out the mass flow rate of strong solution, which is nothing but circulation ratio into mass flow rate of refrigerant, which is equal to 0.9193 kg per second. And mass flow rate of weak solution, this you can easily obtain from the mass balance across the absorber, and we have shown that this is nothing but circulation ratio plus 1 into mass flow rate of refrigerant. Okay. So, if you are substituting these values, you find that mass flow rate of weak solution is nothing but 1.05 kg per second. Obviously, the difference between the weak solution flow rate and the strong solution flow rate should be equal to refrigerant flow rate, okay, because the mass has got to be balanced. So, we have found the required properties. Now, required mass flow rates. Now, let us find out the heat transfer rates at various components. Okay. Evaporator QE is equal to 300 kilowatts. This is the information given in the problem itself. Then let us come to the absorber, and from energy balance of the absorber, what is how do you write the energy balance of the absorber? So, this I have explained many times. You just take control volume across the absorber, energy coming in is energy going out, and we want to find out QA. Okay. So, if you are writing energy balance, you find that energy going out is nothing but QA plus mass flow rate of weak solution, that is at 0.5 into enthalpy at 0.5. Okay. This should be equal to energy coming in. So, energy is coming in by the way of mass flows. So, energy coming in is m into H1, this is nothing but the energy contained in the refrigerant plus m strong solution into H10. Okay. So, this is the energy balance for the absorber. So, from this equation we can find out QA, because we know all these mass flow rates and enthalpies. Okay. So, from energy balance QA is equal to mH4 plus MSS into H10 minus MWS into H5, and all the mass flow rates have been computed and all the enthalpy values are known to us. So, if you simply substitute these values, you find that the required heat rejection rate at absorber is equal to 354.74 kilowatt. Similarly, you apply the energy balance for the generator. For the generator, if you write the energy balance, again you can take okay. So, we take again the control volume across the generator. So, from this you can find that energy coming in is equal to energy going out. Energy going out is m into H1 plus M8, that is m strong solution into H8, right, and energy is also coming by the way of weak solution, this is MWS into H7. Okay. So, this is the energy balance across the generator. Similarly, let me explain energy balance across the condenser and all, so I need not come here again. So, from energy balance across the condenser, you find that QC is equal to m into H1 minus H2, and energy balance across the expansion device is nothing but H2 is equal to H3, and across the evaporator we have already shown QE is equal to m into H4 minus H3. Okay. So, from this we find that energy balance is mH1 plus MSS into H8 minus MWS into H7. As if you remember, I said that H7 enthalpy at 0.7, that is the weak solution enthalpy after solution heat exchanger, has got to be obtained from energy balance across the solution heat exchanger. Okay. So, let me give that equation. So, enthalpy of weak solution at the exit of solution heat exchanger is obtained from the energy balance equation, and the energy balance equation for the solution heat exchanger is very easy. energy gained by the weak solution is equal to energy lost by the strong solution. That is what is shown here. Energy gained by the weak solution is MWS into H7 minus H6. This is equal to energy lost by the strong solution, that is MSS into H8 minus H9. So, this gives H7 is equal to H6 plus MSS into H8 minus H9 divided by MWS, and we know everything on the right hand side. That means we know all the enthalpies, we also know the mass flow rates. So, if you substitute these values, you find that the enthalpy is minus 37.5 kilojoule per kg. Now, if you substitute this enthalpy value in the energy balance for the generator, you can find out what is the required heat input to the generator QG. Okay. So, we find that QG is 380.54 kilowatts. So, this is the energy that is to be supplied to the generator. Then condenser, as I have already explained, QC is equal to M into H1 minus H2. M is the mass flow rate of the refrigerant known to us. H1 and H2 are enthalpy values which are also known. So, if you substitute these values, you find that heat rejection rate at condenser is equal to 325.9 kilowatt. And solution heat exchanger. So, if you write the energy balance I have just explained to you, from the energy balance across the solution heat exchanger, QSHX is equal to energy lost by the strong solution, that is strong solution flow rate, which is equal to refrigerant flow rate into circulation ratio, that is M lambda into H8 minus H9. This should be equal to energy gained by the weak solution, that is M into lambda plus 1 into H7 minus H6. Since everything is known to us, we can substitute these values and you find that heat transfer across the solution heat exchanger is 122.3 kilowatt. And so, we got all the required energy transfer rates across each components. You can check the overall energy balance. What is the overall energy balance? Okay, so overall energy balance is energy supplied to the system should be equal to energy rejected by the system. So, energy supplied by the system is nothing but QG plus QE, because you are supplying heat to the generator and evaporator is extracting heat from the low temperature heat source. So, energy into the system is QG plus QE. What is the energy rejected out of the system? Out of the system is energy rejection is taking place at the condenser, that is QC, plus heat rejection is also taking place at the absorber QA. So, QG plus QE should be equal to QC plus QA. If this equation is satisfied, that means your answers are correct. Okay. So, you can easily check QG plus QE is equal to 380.54 plus 300, which works out to be 680.54. And what is QC plus QA? QC plus QA is 325.9 plus 354.74. So, this works out to be 680.64. So, you can see that on the right hand side you have 680.54. On the left hand side you have 680.64. The small difference, the negligible difference is could be due to the rounding of errors or slight mismatch in the property values. Okay. So, this is one very important thing whenever you do the problems. Now, finally, you can check your answers by seeing whether total energy balance is taking place or not. That means, what you have to do is you have to take the entire system as a control volume. Okay, then it becomes a closed system because there is no mass interactions. So, once you take the entire system as a control volume and if you apply the energy balance and if this energy balance is matching, that means your answers are correct. Okay. Now, we have to find the COP and second law efficiency. So, we find the COP by neglecting pump work, because I will show you that the pump work is really negligible. So, COP is defined as QE divided by QZ. QE is 300 kilowatts, QG is 388.54 kilowatts. So, the COP is found to be 0.7884. And second law efficiency, as you know, is nothing but the ratio of COP of the system divided by the maximum possible COP, that is nothing but equivalent Carnot COP. Okay. So, for a 3 temperature system, the maximum possible COP is nothing but the ratio, nothing but the product of a Carnot reverse Carnot refrigerant system into a Carnot heat engine system. This is what we have shown in fact. Okay. So, COP Carnot is nothing but TE divided by TC minus TE into TG minus TA by TG. Okay. And all the temperatures are known to us, all 4 temperatures. So, if you substitute these values, you find that the maximum possible efficiency is 1.129. So, the second law efficiency is the ratio of these two, which is found to be 0.6983. Okay. This second law efficiency value is quite high, because here we have assumed the solution heat exchanger to be 100% effective when, but in actual this thing it may not be the case. Okay. And there will always be pressure drops and all that. As a result, the actual COPs will be little lower than this. Finally, we have been asked to find out the solution pump work. For finding the solution pump work, we assume the solution to be incompressible. So, once you assume the solution to be incompressible, work input to the pump is given by integral VdP. Okay, so integral VdP is V solution into P6 minus P5. This is P6 minus P5 divided by the density. Density is given as 1200 kg per meter cube. Okay. So, from this value expression you can find out the specific work input to the pump. Okay. This is found to be, there is a small this thing here, this is actually kilojoule per kg. Okay. So, because and if you want to find out the actual work input to this, you have to multiply this. So, the actual work input W is Wp into weak solution flow rate. Okay, you multiply that into weak solution flow rate. So, if you are multiplying this into weak solution flow rate, you will find that weak solution flow rate is about 1. Okay, 1 kg per second. Okay, so you will find that this is almost equal to 0.01 kilowatt. Okay, which is really negligible. Okay. So, this is the typical problem on absorption systems. Okay. The procedure is almost same as compression systems, but absorption system is little more complicated, because you have to deal with the solutions and you have to find the properties of refrigerant as well as solutions. Okay. For that you have to have PTX and HTX data. Okay. Once you have the data and once you identify the state points properly, you can easily calculate the required performance parameters. Okay. So, these are two typical problems. Now, let me give the answers to homework problems. The first problem, if you remember, was a problem on gas cycle refrigeration system, and I have worked out a system working with air as a working fluid, and I asked you to rework the problem by replacing air with helium gas. Okay. And the only difference between these two is their properties, because rest of the temperatures and pressures are same for both the systems. Okay. So, what are the differences in properties? For air, the specific heat Cp is 1.005 kilojoule per kg Kelvin, and the specific heat ratio is 1.4, whereas for helium gas the specific heat is 5.193 kilojoule per kg Kelvin and specific heat ratio is 1.667. Okay. And the procedure is exactly same as what I have shown in the last lecture. Okay. So, if you follow the exact procedure and if you take these property values of helium, then you will get the answers. Okay. So, I will show you the answers. In fact, I will show the not the answers only, but I will show the comparison between the air cycle and the helium cycle. Okay. First, you can look at the system with regenerative heat exchanger. Okay. That means both the cycles use regenerative heat exchangers, and if you remember in the problem it was mentioned that the regenerative heat exchanger had an efficiency of 0.8, that is effectiveness of 0.8. Okay. Now, the first column shows the performance with air and the second one shows with helium gas. Okay. So, first you can see the temperature at compressor exit. With air it is 546.4 and with helium gas it is 711.1. Okay. So, that means there is a big jump in the exit temperature, which is actually a negative this thing as far as helium gas system is concerned. This is happening because helium has much higher specific heat ratio compared to air. Okay. Next is temperature at turbine exit. Temperature at turbine exit with air is found to be 131 Kelvin and with helium gas it is found to be 100.7 Kelvin. Okay. So, the high specific heat ratio is advantageous here, because for the same inlet temperatures you get a lower turbine exit temperature with helium gas. Okay. So, this is an advantage. And the mass flow rates, there is a big difference between air system and helium system, because for the same refrigeration capacity helium gives you larger temperature difference, that means larger refrigeration effect, because of two reasons. The first reason is it has much higher Cp compared to air. Air has a Cp of 1.005, whereas helium has a Cp value of 5.193, that means more than 5 times. Okay. In addition, the delta T is also slightly higher. As a result, you find that the required flow rate with helium is much lower compared to air. Okay. However, the required volumetric flow rate for air is lower than helium. This is because helium has much lower density compared to air. Okay. Next, net work input. Net work input is there is a big difference because the compressor exit temperature is very high for helium and Cp value is also high. You find that required work input to the compressor is very high, even though the mass flow rate is low. Okay. So, as a result, the COP of the system is less with helium gas. Okay. So, you can see that by replacing air with helium, you are gaining by way of lower turbine exit temperatures and lower mass flow rates, but you are paying by means of higher lower COPs. Okay. Next, without regenerative heat exchanger, again you can see the performance trend is almost same. With air you get a exit temperature of 469 and with helium you get about 610 degree Kelvin, and temperature at the exit of the turbine is 151.76 with air and 116.6 with helium gas, and mass flow rate is again about 1.1 kg per second with air and it is 0.1523 with helium, and volumetric flow rate is 0.7606 with air, 0.7687 with helium, and net work input is 93 with kilowatts with air and 151 kilowatts with helium. COP is 1.074 with air and 0.661 with helium. Okay, so this is the performance comparison. Second problem was the comparison between SSS Vapour Compression System working with R134A and with ammonia. Okay, and for the same evaporator and condensing temperatures and isentropic compression. The evaporator temperature is given as minus 25 degrees centigrade and condensing temperature is given as 50 degrees centigrade. So, again here the performance comparison is shown. In fact, this is for R134A I have worked out in the last class. Okay, so I asked you to work out for ammonia. You can see that refrigeration effect for ammonia is very large compared to R134A. Okay, so as a result the required mass flow rate will be very low with ammonia. This is a plus point, and work of compression is also quite high for ammonia, and superheat horn is in fact negligible in case of 134A, it is only 0.2 kilojoule per kg, whereas it is very high in case of ammonia. This is because ammonia has a symmetrical vapor dome on TS diagram as explained in the earlier lectures. Okay, and throttling area is also quite high for ammonia compared to R134A, and COP is marginally higher for ammonia compared to R134A, and compressor exit temperature is very high with ammonia. In fact, this is a major problem in ammonia systems. Okay, whereas with R134A system it is quite low, right. So, from this we can easily conclude that refrigeration effect and work of compression are much higher for ammonia. This means the required refrigerant mass flow rate is much smaller in case of ammonia, and losses due to superheat horn are much larger in case of ammonia, whereas they are negligible in case of R134A. This is because of the differences in the vapor dome on TS diagram. Okay, and throttling losses and superheat losses are of same order of magnitude for ammonia. Okay, and COP is marginally higher for ammonia, and compressor exit temperature is much higher for ammonia compared to 134A. Okay, so these are the conclusions by comparing the results of ammonia and 134A. Now, let me quickly give the answers to the objective type questions. I asked you which law of thermodynamics is a directional law, and the choices were first law, second law, third law and fourth law, for third law and zeroth law, and the answer is second law. So, second law of thermodynamics is a directional law. Second question was, according to second law of thermodynamics for a system undergoing a process, whether entropy of system cannot decrease or entropy of the system cannot increase, or the sum of entropies of system and surroundings remains constant, or the sum of entropies of system and surroundings always increases. The answer is D. That means, according to second law, the sum of entropies of system and surroundings always increases. This is the law of entropy increase. Okay. Third question was, expansion of a liquid always results in a significant temperature drop when the initial condition is in subcooled state, B the initial and final conditions are in subcooled state, C the final condition is in two phase region, and D none of the above. The answer is C. That means the final condition should be in two phase region. That means some flashing of the liquid should take place for significant temperature drop to occur. And fourth question was, during isenthalpic expansion of a real gas with a negative Joule-Thomson coefficient, what happens to the final temperature of the gas? the answer is the final temperature is higher than the initial temperature. Okay. So, when you have negative Joule Thomson coefficient for real gas, the exit temperature will always be greater than the inlet temperature. Finally, I asked you the COP of a completely reversible single stage refrigerant system depends on what? The answer is it depends only on the evaporator and condensing temperatures. It does not depend on pressures, it does not depend on the working fluids, it is only a function of temperatures according to your Carnot's hypothesis, okay, Carnot's theorems, right. Now, let me give them quickly one homework problem. The problem is like this: in a steam jet refrigeration system, the ejector extracts 3.3 meter cube per second of saturated vapor at a temperature of 7.2 degrees centigrade from the flash chamber. The return water from the cooling coil at a temperature of 15.6 degrees centigrade is sprayed into the flash chamber, while the makeup water enters the flash chamber at a temperature of 21.1 degrees centigrade. So, all that we have to do is find the cooling capacity of the cooling coil. Assume the pump work to be negligible. Okay. Let me show the schematic. So, this is the schematic of the homework problem. Here you need not bother about the steam ejector working and all that. What is asked is what is the refrigeration capacity of the cooling coil. Okay. So, all that you have to do is apply mass and energy balance across the flash chamber and apply mass and energy balance across the cooling coil. Okay. So, if you are applying this, then you can easily find out the required answer, and you can use this property data for water at various points. The property data is given like this: state point 1, temperature is 7.2 degrees centigrade, pressure is 1.0285 millibar, enthalpy is 2510 kilojoule per kg, specific volume is 129 meter cube per kg. Similarly, at point 2 you have temperature 7.2 degrees centigrade, enthalpy is 30.2 kilojoule per kg. Point 3, temperature is 15.6 degrees centigrade and enthalpy is 65.4 kilojoule per kg. Point 4, temperature is 21.1 and the enthalpy is 88.4 degrees 4 kilojoule per kg. So, this information is sufficient for you to work out this problem. I will give you the answer to this problem in the next class. Okay, thank you.